All right, thank you for the invitation to speak, and thank you to Paolo and Charlene for organizing. So I'm going to give an update on, I guess, what's now been a somewhat long project and a number of papers on complexity growth and saturation. And specifically, I'll be mostly talking about two papers. One which is from, I guess, 2 years ago now, which was joint work with Fernando Brenda, with Jim Hassani, Richard Kuhn, and John Freskel. And a lot of the key ideas and techniques in that paper are due to Richard Kuhn, which are here. And I'll also, on the update side, try to give an overview of an upcoming work with Michał Ośmanec and Michał Horodecki, which hopefully should appear this month. So in the first paper, which maybe some of you have heard me talk about before, is more about the complexity growth aspect of quantum complexity or circuit complexity. And then the second paper is more about saturation and recurrence. So I'll try and touch on all the ideas and sort of the techniques that are used in proving all these things. So just to give a really quick TLDR about what we know and what we can prove about random quantum circuit complexity growth. And I'll define what I mean by random circuits, and I'll define what I mean by complexity very precisely in a minute. It's a little blurry, but hopefully I'll read out the symbols. But right, so the idea is that for some random circuit, we have circuit complexity, and it's going to grow for an exponentially long time and then saturate. So if you've heard me talk about this subject before, you've probably heard me talk about this growth regime and using these nice things called unitary designs to prove growth. I'll kind of review that in the first part of the talk, and I'll review how you prove complexity growth. And then in the second part of the talk, I'll talk about basically how you can get a linear growth at late times, and then how you can prove saturation, and moreover, how you can prove the existence of recurrences at doubly exponential times. And they all sort of use slightly different techniques and make use of some nice ideas in quantum information. So that's basically, in a very brief sense, what I'll discuss. Yeah, good. Okay, so quantum complexity is a very well-established notion in computer science and quantum information. And it sort of allows us to distinguish tasks which are easy versus hard for a quantum computer. But there's been a lot of interest in the quantum circuit complexity more recently in quantum many-body physics, where the idea of complexity of specific states has been used to distinguish topological phases. So you ask about the existence of some shortcut circuit given some state, which takes that state to a trivial state. And probably of more interest to the people in this room, there have been conjectures about the circuit complexity of specific CFT states, and basically their long-time dynamics are conjectured to know something about the interior of ADS black holes. But much more generally, and sort of a little bit more interest to me, I think this idea of complexity growth extends beyond ADS CFT, and is in some sense like a universal aspect of chaotic systems. So if you take a bunch of quantum mechanical degrees of freedom and make them interact with each other, you can ask questions about universal properties and their real-time dynamics. And these are things we like to call like thermalization or many-body quantum chaos or scrambling. And I think complexity growth is just sort of one universal feature of chaotic dynamics. And understanding its relation to all these other different like sort of probes or diagnostics of chaos is sort of work to be done. And what I mean by complexity, I'll define it precisely in a few slides, but just to give you a very intuitive notion, the traditional definition of circuit complexity involves basically fixing some set of universal gates. So these are some easy operations which you can maybe perform on your quantum computer. So these are, like I'll always use two local gates, but these are just, if you have some array of qubits, you have some simple gates which are easy to apply. You have some set of those gates, and given some target unitary or some target state, you want to build a circuit which approximately implements that unitary or approximately prepares that state to within some tolerance. Okay? And then the circuit complexity is the minimal circuit which does that. So it's the smallest circuit which achieves that given some tolerance, delta, and given some universal gate set. And in this sense, it sort of quantifies like how hard or how easy that unitary is, right? And just to fix some notation, in this talk, I'll be considering systems of n qubits. So I'll always be working with finite dimensional Hilbert spaces. And specifically, I'll have n qubits of local dimension q, because sometimes it'll be a useful knob to turn. such that my total Hilbert space dimension D is q to the n. Okay? So these are, there's maybe one more important parameter in this talk, but yeah, we'll have, just to reemphasize, n qubits. So q will sometimes be 2 if I'm talking about qubits, but more generally I might leave it as some parameter q. And the total Hilbert space dimension is lowercase d. So are there any questions about the rough intuition of what complexity is before we proceed? Okay. So it's believed, conjecture, that the complexity of a simple initial state, so take some unentangled product state, say, grows possibly linearly under time evolution by a chaotic Hamiltonian, where you get this stream that's supposed to be a negative IHT, because the resolution on this border isn't great. But this is a linear growth for an exponentially long time, up to a time which is exponential in the number of degrees of freedom. So we grow linearly up to a time which is like e to the n, after which we saturate. But this intuition extends, or this belief extends to the unitary time evolution itself. So we have some unitary operator, e to the IHT, and the idea is that the circuit complexity of this operator also grows linearly in time for an exponentially long time, saturating at the time scale which is like e to the n. And actually computing this complexity analytically is extremely hard, specifically for some fixed h, because naively you just get some idea of what the complexity is. You sort of, sounds like you need to enumerate all possible circuits to find what the shortest one is. Right? Yeah.
Is the time scale which you saturate independent of like the local system dimension q?
No. Right. So yeah, I'm sort of using like high energy notation here, but it should be like it should basically be d squared. So it should be like q to the 2n. Yeah. So basically all through this talk, except for in one counterintuitive place, I'm just going to assume q is some fixed number, like which is like which I'm not taking to be large. I will take it to be large ones. So every time I have an e, I think you can always mentally replace it with a q if you want. Any other questions? Right, so computing this analytically is extremely hard because naively you need to enumerate all possible circuits to find out what the shortest one is.
Sorry.
Yeah.
Two things. One, when you mean complexity of the minus HT, you just mean the complexity of the state that evolves. So
No. Right. So we could, basically everything I'm going to say applies equally to states and unitaries themselves. I think it's a little bit, somehow there's less baggage if we just talk about the unitaries, so I'm just going to focus on the unitaries. Somehow the techniques are a little nicer. I'm really talking about the complexity of the unitary itself.
So the circuit is simulating the unitary.
Yeah, basically there's no initial state. It's just the initial state's like the identity. Yeah. So you have some unitary U, and you're asking like how can you apply little local unitaries to build up that unitary? And there's no state. We could also talk about the complexity of states, and basically everything I'm going to say also works if you just have an initial state. Good. But yeah, I'm basically just going to focus on the complexity of unitary operators themselves. Right, so computing this analytically is very hard. So basically, before I describe how we approach this problem, I'll just give you some intuition about why we expect this thing. So we expect some polynomial, or possibly linear growth, because sort of the complexity should scale with the time we evolve for. And we expect that shortcuts should be rare. And by shortcuts, I mean, if you're given some evolution to some time t, it should, for a chaotic system, it should be rare that I'm able to prepare that unitary with a substantially shorter circuit. Okay? So in this sense, I mean, like, collisions should be rare. And more precisely, there's this nice body of literature called Hamiltonian simulation, and it sort of gives you upper bounds, right? So it sort of gives you a way to construct a circuit which approximately prepares your time evolution, right? But there's no guarantee that it's optimal, but at the very least it's an upper bound. So the idea is you just take your e to the IHT, you trotterize it, and then you decompose those trotterized steps using Solveig-Kitaev into your local gate set, and that gives you some circuit which implements your unitary evolution. And basically known simulation algorithm scale polynomially or possibly linearly with time. So you can just view that as like an upper bound of what you expect. Good, so that's why you expect some growth regime. The reason you expect it to saturate is just that there are only a finite number of unitaries. So the unitary group is continuous, but if we just sort of discretize and count the number of delta balls in the unitary group, you can quickly convince yourself that there should be a doubly exponential number of those. So something like 1 over delta to the 2 to the 2n. distinct unitaries, right? So delta distinct unitaries. And if you just proceed with the counting argument and count the number of exponentially deep circuits, you realize that the number of depth, e to the n circuits is comparable to the volume of the unitary group. So you expect that, basically collisions need to start dominating in exponential times as you sort of fill up the unitary group. Yeah, please.
I don't know if this is just an artifact of the image, but sort of what is setting the scale for those like fluctuations after the saturation?
Yeah, so for some, right, I mean, I just sort of made it wiggly because I but like yeah, so for some fixed h, you do expect there to be some slight wiggles, probably because, maybe like, the evolution, if you have some circuit, maybe you accidentally like apply an inverse gate and it occurs like a tiny, tiny amount. So there's a separate question about what the scale of the fluctuations is, right? You can always come up with a very strict upper bounds and lower bounds, but the complexity itself might wiggle a little bit. And the scale of those fluctuations is probably something that depends on time. And I think there are a number of open questions there.
Depends on the size of the fluctuation.
Hmm?
It depends on the size of the fluctuation.
Right,
Because
yeah,
the fluctuation goes up on E2, E3.
Yeah, but at some point the fluctuations need to get large as you approach recurrence time. So there's like I think in terms of like rigorous results, I think proving bounds in the size of fluctuations at given time scales is not 100% known. But yeah, I expect like basically before exponential times they're like order of fluctuations, and then if you wait a very, very long time, they can get larger. So this is why you expect it to grow and saturate. And in order to make progress, there are a few things we can do. We can use complexity theoretic assumptions to, make statements about like the complexity of particular Hamiltonian evolution. So the idea is you just like construct some artificial Hamiltonian, encode some problem you know is hard, basically based on some complexity theoretic reasons, like p space doesn't equal BQP or something. And then that allows you to prove lower bounds, so you can, this is sort of the approach taken by Aronson and Susskind as well as Bogdanovich and Brandau, that at super polynomial times, at exponential times, the complexity needs to be super polynomial. And this is just basically, you just took a hard problem and you've encoded it in your Hamiltonian. So this is sort of one approach you can take. The other approach is you can focus on ensembles of time evolutions. And this is what I'm going to talk about today. So I'm going to focus on random quantum circuits. So the kind of toy model of chaotic systems I want to consider are these random quantum circuits. So this is some time-dependent evolution, which is defined of n qubits of local dimension q. Yeah? And you could imagine evolving with, say, staggered layers of two-set unitaries. But the point is, you fix some universal gate set, and each unitary here is drawn randomly from that gate set. And where time evolution to time t is given by like a product of your t layers. So t here is the depth of the circuit. Time is the depth of the circuit. And the goal is to try and prove something about the growth of complexity in this model. And just sort of, if you've sat through random circuit talks before, you might have seen people always use these brickwork circuits, but for me, actually, that's not going to be important at all. You can basically consider, for almost everything I'm going to say in this talk, the results will hold if you just consider very general sets of random circuits. So you just take some graph. Basically, as long as it's like sufficiently connected, everything I'm going to say works. It doesn't need to be 1D, or it could be all-to-all, that's fine. It'll change the scaling of something slightly, but it's not really important. And moreover, the gates don't need to be random. They can just be drawn from any universal gate set. Actually, very general universal gate sets work. So for random circuits in this talk, you could consider various models, these brickwork, like single gate per time step, various graphs and various universal gate sets. Everything I'm going to say actually works out fine. Like a very small caveat. Any questions about the model I'm considering?
That's the low closing engine, right?
This is still 1D.
Like, for example, on the right two qubits.
Yeah. Well, it's wait longer, then it'll get connected. So the idea is, yeah. So in this model, there's some uniform probability over all edges in the graph that you draw gates, so it'll become connected if you wait long enough.
So the result persists as long as the number of sites involved in a single gate is not scaling as.
Oh yeah, that's a good point. I'm always going to consider gate sets which are too low.
But how about 3 or 4?
That's
first time.
Yeah, that's fine. I mean, everything should sort of get easier the more, right? Like, if you consider these as like small random unitaries, the more non-local you make it, the better everything gets, and like the
Yeah,
faster
yeah,
complexity, right? If I just apply one random unitary, I maximum complexity instantly. So I would say that if you, everything I'm going to say is like a lower bound. I think that's true. But yeah, strictly speaking, all my results are going to just like work with two local gate sets. And specifically, it's been conjectured that most local random quantum circuits of depth t have a complexity which scales linearly in time for an exponentially long time. So proving this exactly linear growth is sort of like the, is known like holy grail of the subject. And again, this sounds perfectly reasonable, right? Like if I just use the same gate set G to define complexity as I've actually like drawn this circuit, then it just seems like this circuit should be, it's like its own complexity. But again, the difficulty is you need to prove that this is the shortest circuit. So you need to enumerate all circuits of that depth and like show to me that that was actually the shortest or like the minimal implementation of that, minimal instantiation of that circuit. Okay. And I'll just mention that like there is a slightly other approach you can, another approach you can take, or kind of another relaxation you can take to actually prove things. And this was done in this paper by Haferkamp et al. And there they focus on the exact circuit complexity, which is a little bit artificial. But it turns out if you just focus on the exact complexity, you can prove things a little bit. You can get slightly stronger. You can get some stronger results and actually prove this linear growth. But just to again give a quick recap of what I'm going to show. So this pink line here is the behavior we expect, and this blue line is what we can prove. So basically, you can prove and this is for qubit circuits. So local dimensions too. So you can prove some algebraic growth, which is slightly sublinear, and then you can show that the linear growth does kick in at late times, and there is a saturation at an exponential time, but it's like a little bit bigger than what you expect. And sort of as you keep like working hard and you keep kind of improving some of the like results that this is all built on, you kind of keep you push the slope up a little bit, and you bring the saturation time a little bit forward. So I'd say like progress is that like this blue line is like slowly approaching the pink line because we're nailing things down better and better. But
So the blue line is the lower bound?
blue line is, these are lower bounds that we know, and then this is what we expect. And sort of, over the last few years, I'd say that this blue line has sort of like gotten better and better as we've sort of been nailing things down a little bit better. And this is for random circuits, but basically the techniques I'm going to overview, I think this is sort of a framework to prove complexity growth for any time-dependent model. So if you have something like your favorite spin system with disordered couplings, and you make those couplings a little bit time-dependent, everything I'm going to say should work. So Brownian expectation. Yes?
Is there anything expected different in time independent models?
No, I mean, I expect it to do the same. It's just like the way I'm going to prove things, like, I think you need to be a little smarter than just, I think like probably some new ideas are needed. Whereas like the framework I'm going to show should sort of work. I mean, it might be hard, but it should sort of work for any time-dependent system. You expect the same thing for time-independent systems. It's just, I would say we don't have the right techniques.
This is about on the average or the probability of minus?
Yeah, right. So I'm talking about ensembles, and it's a fantastic question. So what I mean is with extremely high probability over the choice that we get. So for a given instance, with probability exponentially close to 1, I'll give persistent. And I won't mention this much, but if you take the local dimension to be larger, you get something which is like better. So if you take the local dimension to be large, you get a linear growth for some time, and you also get the saturation time to be better. So basically taking the local dimension to be some large constant, say, everything gets a little better. Okay, so first I'll define complexity, and then I'll talk about unitary designs, and then how that's related to complexity of local random circuits. And then sort of at the end I'll talk about like a sort of different set of ideas which allow us to prove saturation or recurrence. How many minutes should I go over? Just to...
Until 10:47.
Okay, that's fine.
Good question.
Yeah. So, good. So again, we're considering a system of n qubits, and just to have to reemphasize what I mean. The complexity of a unitary is the minimal size of a circuit built from those elementary operations, which approximates that unitary. So we have some universal gate set G, and let G sub R denote the set of all circuits of size R. And then just to be rigorous, we say that a unitary has delta complexity equal to R if we minimize over all basically size R circuits, which approximate that unitary to within that tolerance with respect to some norm. And the norm I'm going to use is some fancy thing called the diamond norm, but it's not that important. Right, so there's just some distance, and we're close. You know, the sort of the minimal circuit is just close to our unitary with respect to that distance. There's a stronger definition one could consider, and stronger in the sense that being close in this implies the standard circuit complexity, and this has involved some nice ideas in terms of optimal measurements, but for the purposes of this talk, it's not that important. It just sort of makes everything harder to do. But I think there's some reasons why this idea of complexity in terms of measurements might be like a better way to think about it for some reasons involving ADS-CFT. Right? I think this sort of makes more sense from some intuition from ADS-CFT, but maybe we can talk about that after. Good. So again, we're interested in the complexity of random quantum circuits. And to make progress, I want to derive some very general statements about the complexity of these nice sets of unitaries called unitary designs. But before I do that, I need to tell you what a design is. So I'm going to give like the rigorous definition before I draw some pictures, which I think are much more intuitive. So recall that the Haar measure is the unique left and right variant measure on the unitary group. If we consider some ensemble of unitaries, which I'll denote with this curly E here, maybe I should have written this separately, but I'm going to be interested in ensembles of unitaries. So this is just some set of unitaries with some probability. We're often interested in moments of that ensemble, and sort of one way to encode moments, or like sort of polynomials in those unitaries, is with this operator called the k-fold channel, which is basically encoding the k moment. And we say that we have an exact k design. We say some ensemble of unitaries E is an exact k design if these moment operators are equal for all operators of. Exactly equal to the Haar measure. And that's basically their existence proofs, but for general k, so I should say that like Pauli's are an exact 1 design and Clifford's are an exact 2 and 3 design. But for general k, very few constructions are known. So in quantum information, we often like to consider approximate designs. And these are just, this is an ensemble of unitaries, for which the k-fold channels are close in some norm. Okay. And designs are very powerful or very useful notions in quantum information because they sort of allow you to implement full Haar randomness with like relative efficiency. So you can get all these nice Haar random results without having to like apply exponentially deep circuits. Okay. So more intuitively, we say that an ensemble is an approximate design. If the average over that ensemble is close to the average over the full unitary group up to the k point. So you should envision some like set of unitaries, the unitary group, some set of points distributed on that group. We're averaging over that set of points, like we're averaging some polynomial in U and U dagger over that set of points. And we're saying that that average is approximately equal to the average over the full group. Okay? And that's all the design is, up to the k point. So for any polynomial involving like KUs and KU daggers. Any questions about what a design is? Basically just like nice like distributions of unitaries on the unitary group which look Haar random if you don't look too closely. And the closer you look is sort of the higher the k is. So another intuitive way of thinking about what a design is you can ask how random the time evolution of a system is. This is sort of what we're doing now. So you consider some ensemble of time evolutions. Those might be random circuits. Those could be your favorite disordered spin system, so e to the IHG with disordered h's. So time equals 0, it's just a bunch of points sitting at the identity. But chaotic time evolution is going to move us rapidly and ergodically over the unitary group. So we can kind of quantify how random the time evolution is by asking at what time t do those points start like moving around and look really well distributed and start approximating moments of the unitary group. So that's another way to think about it as design. I'll pause again for questions. Any questions about what a design is? Good. So what one can ask is, this is, I told you these are very nice ensembles of unitaries. You can ask, does the structure of a design allow you to say anything about the complexity of the design elements? And the answer is yes, and I'll just give two informal statements. Basically, you can say, or you can prove that with extremely high probability, so something like basically exponentially close to 1, a unitary drawn from an approximate design has complexity which is approximately equal to like n times k. So it scales linearly in k. And then you can also, so that's a probabilistic statement of the design. You can, if you're worried about some pathological case where like one design element was occurring with high probability and had high complexity, but everything else was, sort of saying something with high probability isn't quite the same as saying most. So you can basically establish that most, most unitaries in your design actually have this complexity. So the precise statement is something like, here an exponential number in k distinct unitaries with that complexity. But the idea is that it's not just with high probability, it's like most of the things in that set have complexity which scale linearly in k.
And that's the counting argument?
I mean, it depends. I don't know. It depends what you mean by counting argument. You use it's a counting argument, and you use something called you use a union bound. But I mean, it's basically like a fancy. It's yeah. There are a few different ways you can prove this. The easiest is just sort of a simple application, something called Markov's inequality, where you can bound probabilities using expectations, and you design expectations really, really tightly, and that allows you to prove probabilistic statements. It's like you can boil down at least this first thing to like a one-page proof or a two-page proof. It's a little fancier than a counting argument, but you are secretly relying on the fact that there are lots of things in the design. But a counting argument doesn't really work. So if you just give me a set of unitaries and you say there's like a billion of them, like I don't know that they're not all sitting at one point, right? They could all just be sitting at the identity. So you sort of need to be a little fancier than a counting argument. A counting argument because you need to like sort of prove that they're spread out. It depends what you mean by counting argument. That's a sort of answer. Are there any other questions about it? The more precise statement is just that with probability greater than 1 minus something exponentially small, a unitary drawn from a design has complexity lower bounded by this expression. So this is just the explicit dependence on the delta approximate, or so the epsilon approximate design, as well as the delta that appears in the definition of complexity and the gate state you choose. It's all sort of very weak logarithmic dependencies. So the important thing to keep in mind is it's just linear in k, which is the degree of the design. Okay, so back to the idea. We wanted to prove something about random quantum circuits. And what we did is we showed that designs have some complexity. So we're going to make progress by now showing, or I guess relying on old results, that random circuits form designs. So it's known in this very seminal result by Brandau, Harrow, and Borodetsky that basically polynomial in K, depth random quantum circuits form approximate unitary designs. And the key thing here is that basically just random circuits of depth linear in n and this high degree polynomial in K, so it's K to the 11, form approximate designs. Right, so we can combine this just to give some statement about the complexity of random quantum circuits, these local random quantum circuits. And with very high probability, a local random circuit of depth t has a complexity which is scaling basically this algebraic power of t. And then you can also show that there are a lot of those distinct unitaries in the set with that complexity. So this establishes some polynomial relation. Right, we have some t to the 1/11. But what we really wanted was a linear growth. And just to reemphasize, so what we did is we showed that complexity is linearly related to k. So complexity is going like k. And then we used this BHH result, which said that t goes like k to the 11, which allowed us to extrapolate the complexity must be at least scaling like t to the 1/11. Okay. And I'll just briefly mention that, like, basically, what I mean by general framework, this is sort of a general framework for proving things, is that anytime you have some set of time evolutions which is forming design, you just throw this at this complexity result and then you prove complexity growth. So it's known that these kind of Brownian quantum circuits, these are like local spin systems with disordered time-dependent couplings. It's known that they form designs. So that gives you some bound on the complexity growth. There's also some kind of nearly time-independent model, which is also known to form designs, depending on how that at all. And then, yeah, I should probably update this, but it's also known that very, very, very general random quantum circuits with very general gate sets and on any sort of lattice also form designs. Good. But to get a linear, like one way to prove a linear growth in complexity is to prove a linear growth in design, so that T is scaling linearly in K. And moreover, a lower bound on the K design depth is known to be linear in N and K. So one way to prove linear complexity growth is to prove that random quantum circuits are sort of optimal implementations of unitary designs.
So can I just get the result that you have proved, which is that the average complexity after a time t is must be at least as big as t to the 1 over n?
Yeah, I'll prove on that, but it's sort of a little better than average. It's sort of given some random quantum circuit. It's with extremely high probability that that particular circuit has this complexity. So it's basically, you might get, if you just pick a random circuit at random, you might get extremely unlucky and pick all the identities everywhere.
Yeah.
Right. And then
But that's very exponentially right.
yeah, right. So you're saying with exponentially high probability, like 1 minus e to the minus n, that this that the design element will have complexity, k, or lower bound of a k, or like the random circuit will have complexity lower bound of t to the 1 over 11. And then sort of there are a few things you can improve these design results, and that will improve the t to the 1 over 11. So you can, there are a few different ways you can push that closer and closer to linear. Because that's a lower bound, right? It's growing a little slower than you expect, and you can improve on that, and you get closer and closer to linear. But yeah, that's right. Are there any other questions about? But yeah, it's a probabilistic statement about like fixed or like given circuits specifically. So there's been a bit of work about actually showing that random circuits are sort of optimal in their k dependence. But mostly what we know is that if you take Q to be large, so Q is the local dimension, you can get linear growth. But really we want to show this for qubit circuits. So it turns out if you take Q to be large in sort of some bizarre uncontrolled way, you can get a linear growth. And if you take it to be large in a very controlled way, you can sort of improve on that a bit. So you can take it to be large in a k-dependent way. You can show that the behavior is essentially optimal in k. So you get a k-dependent design time, or sorry, a linear in k design time. And just to mention kind of the two approaches you do to show this, there's sort of some nice connections to ideas in many body physics. So one way you can compute design depth is by upper bounding the partition function of a lattice model. So this is a nice way to express the distance of forming a design as a partition function of a lattice model. And then you basically just need to like count domain wall configurations in that lattice model to get some bound. And then the other approach one can take is lower bounding the spectral gap of a Hamiltonian. So there's a way to express a different distance to design as a gap on a Hamiltonian, and then you just need to lower bound that gap, and that gives you sort of the time it takes to form design. So these are some very nice ideas involving StatMech or many body physics. And I'll mention a little bit more about gaps in a second. But, right, so this was basically saying that if we take the local dimension to be larger, you can get a linear growth for some amount of time. So this is one way to draw this. Again, this magenta or pink curve is what we expect. And if you take Q to be large, you can get something which is like linear and then has a slightly better slope. But just to mention sort of one thing, one way to get linear growth for qubits is for random quantum circuits, the spectral gap basically enters like this. So you have a distance to forming a design, and you can upper bound that at the expense of some dimension factors in terms of this expression, which is basically 1 minus gap to the t. So this and the gap of this Hamiltonian is sort of something you can actually apply different techniques to get lower bounds on. So this Hamiltonian is what's called frustration free. And that just means that the ground state of that Hamiltonian is also the ground state of each term. The terms aren't fighting each other to lower their energy. and this Hamiltonian has ground state energy 0. So if you know nothing about the gap, then the lower bound of the gap is 0, right? And that tells you nothing here, because if you plug in 0, you're just taking 1 to the t, and if you evolve t in time, you're not getting anything that's exponentially decaying. But if I have any sort of non-trivial lower bound on the gap, that tells me some sort of exponential decay in time to a design. So this is sort of one way of proving convergence to designs is by getting these bounds on the gaps of these Hamiltonians. And there's a beautiful set of techniques for bounding gaps and frustration-free Hamiltonians.
Can you remind me the condition you involve Hamiltonian? Each term involves a number of qubits is order 1, doesn't scale with that?
Yeah, so it's basically, this Hamiltonian isn't really physical, it's sort of just like a trick. So there's like a way to rewrite a distance to a design. It's basically some operator one. There's a way to rewrite that as the gap of a Hamiltonian. And so it's not really like some physical evolution, it's sort of just like something that comes out of playing with math. But
But involve the any condition on Hamiltonian?
yeah, the
Hamiltonian
Hamiltonian,
can involve any qubits, then of course everything is.
sure. So this Hamiltonian is 1D, it's translation invariant. The local terms are basically written like this, where this is sort of the projector onto 2 qubits.
Yeah.
The kth moment projector.
It's not this particular Hamiltonian.
Oh, sure.
Hamiltonian in your framework. What kind of class of Hamiltonian?
For frustration free or for these random circuits?
No, in general, like.
Right. So everything I'm talking about in this talk are time-dependent evolution. And specifically, I'm talking about random circuits. So there's no real. I think that this design approach to proving complexity should work for any time-dependent Hamiltonian that's chaotic. The results I'm presenting are specifically for random quantum circuits. Okay. And random quantum circuits is some time-dependent evolution where you're applying random gates, but it's not really some, and it's local, but it's not really some nice. It's not because you're applying these 2 local gates locally, but it's not. It's not.
Oh,
some nice,
that's only also to.
Yeah, that's right. The random circuits are local on 2 qubits. Yeah.
That's why.
Yeah, right. This Hamiltonian, the locality of this Hamiltonian comes from that, but it's sort of just like a trick to get bound. And it's nice just because gaps are nice to detect. But one thing, go ahead. One thing you can show is that an exponentially small gap, which is k-independent, allows you to prove that there has to be some linear growth which kicks in at very low times. So, really you want nice gaps which aren't exponentially small, but you can prove an exponentially small gap, and it does allow you to prove a linear growth which has to kick in at some late time. So that's it's like one piece of the puzzle, and really you kind of want to know that there's a linear growth at all times, but you do know at the very least from these exponentially small gaps that there has to be some linear growth which kicks in at late time.
Question.
Yeah.
So in the previous slide, you had this inequality.
Mm-hmm.
So if I have a fixed Hamiltonian and I know its gap, can I actually use this bound to bound the complexity?
Yeah, that's right.
Okay.
Yeah. I mean, basically, just if you don't know anything about the Hamiltonian, right? The gap is lower bounded by 0, and then you want this distance to be basically converging, and how fast that distance converts to how quickly complexities grow.
Okay. Yes.
And then basically, so some lower bound on this gap tells you how fast you're converting to a design, which in turn tells you how quickly complexity is growing. And it's some pretty simple series of steps. Yeah, and it can just come from bounding gaps in these pretty nice Hamiltonians. Okay. And in the last 1 minute, I'll just sort of tell you one different tack you have to take to prove saturation. So you know that our random unitary basically has maximal complexity. But these random circuits only really approach hard in the infinite of in the limit of infinite circuit depth. So how do you show saturation to maximal complexity at some exponential time? And what you can actually show is that there's some kind of strong property which happens at exponential times, and that's that these random circuits equidistribute. And that's sort of like a term we invented, or basically a definition. But the idea is that you can ask what the probability of some random circuit being close to some fixed unitary is. And you can also ask what the probability of some hard random unitary being close to some fixed unitary. And basically you say that when those two things become approximately equal, which happens at exponential times, then the distribution is equidistributed. More formally, you say that random circuits assign some measure to balls in the unitary group. And you're just saying that those that volume is close to the Haar volume, sort of upper and lower bounded by Haar volume, so it balls of similar radius. So sort of like locally, volumes look very similar to Haar. And that actually allows you to prove complexity saturation at some time, which is close to what you expect, very close to what you expect. And the same technique also allows you to prove recurrences, because sort of the recurrence time, you can, basically the recurrence should be, right, so once you achieve this equidistribution property, the probability of like walking to a particular unitary is sort of, becomes approximately equal to that the volume is prescribed, or the inverse of the volume is prescribed with a Haar measure. So by sort of knowing this equidistribution happens at exponential times, allows you to prove that recurrences must happen at double the exponential times. And that's sort of like a pretty good picture of like all the aspects of complexity growth. We have this like growth regime, which is not quite linear, but you can keep pushing that down. We know that there's saturation or recurrences, and so I'd say that the nails keep going in the coffin for random quantum circuits, and these sort of techniques, I guess are basically rapidly proving everything we expect to happen. I'll skip the last part, but which I knew I was going to have time for. But basically, just there's one way I think you can maybe see complexity growth in terms of how rare entropy fluctuations are. But feel free to ask me about that. But yeah, I'll just leave out there are a lot of future things I'd like to think about, lots of future directions. Please feel free to ask me about any of these, but I'll end there. Thank you.
There are some pressing questions for the speaker.
I'll ask.
Yeah.
I just want to make sure I understand. So you expect complexity to grow linearly and saturate around the same time, both for a single unitary, like we have e to the minus I8, and for like a random ensemble.
That's right. Yeah, and
The
that's
time
what
scales are the same for both of those?
that's the conjecture, yeah. And the conjecture should basically be the saturation time is like the square root over space dimension. It's like e to the 2n. And this is sort of what you mean by universal property of chaotic systems. So again, it's a conjecture. We sort of know that this is true for some specific time-dependent model. It's just sort of, I think things are harder to prove for time-dependent systems, but yeah, the belief is that this is sort of any chaotic system should happen. So unless you have some really bizarre integrable system with lots of symmetries, maybe then the complexity of saturation a lot earlier. Yeah.
What are some possible applications of both the method and the result?
Right, so designs are really, really useful in quantum information because basically there are all these nice protocols, and you know that Haar random unitaries will do some fancy quantum thing that you care about. But then to actually implement that, like you can't really implement like a Haar random unitary in the lab. So designs sort of give you all this nice firepower because you can do basically there are all these protocols which sort of are designs are random enough to get you what you want. So that's sort of an application of design for quantum information. They pop up everywhere, like quantum cryptography and like quantum sharing theory. And there's also a way, I think, some of the things that the Google experiment actually did rely on their random circuit. So they implemented some random circuit. The idea that it's provably like the task that is provably hard does sort of rely on like that random circuit's ability to like rapidly scramble things, like rapidly generate entanglement and quickly generate pseudo-randomness. Yeah, that's what I was saying.
You want to
No.
let's back at it again.